Okay, so last week then we were looking at how to draw dot structures and that you definitely need to count the number of valence electrons that each atom brings in. And then the atom with the least number of valence electrons will be the one that goes in the center. That hasn't changed. And that hydrogen always can only make one bond, and fluorine can always make one bond, so they can never double bond or be in the middle. They'll always be on an end. And that then on Friday, we talked about trying to give everyone 8 valence electrons. So today we're going to talk about ions versus also exceptions to that 8 octet rule. So first of all, with ions, you do them the same way, but then they have a charge, which is going to change the total number of valence electrons. So for nitrogen, we know that there are 5 valence electrons, and oxygen has 6 valence electrons. So in NO3 minus, we'll have 3 oxygens. So that's 18 and 5. And now that minus sign means that there's one more electron. Okay, if it were -2, we'd add in 2 electrons. If it were -3, we'd add in 3 electrons. So -1 charge means we add in one more electron. So we have 24 electrons to place. So nitrogen has less valence, so it goes in the center. I always try single bonds first, and then give everyone the right number of electrons to see if, so give everyone 8 if they're larger than boron. And let's see if that would be the right number of electrons. So oxygen now has 8 on each, but then nitrogen would need 2 more. So that would be 8 plus 8. Sorry, that's not plus 8. And so that would be 24 plus 2 more. So that has 26 electrons. So that can't be right. It can't just be all single bonds. I'm off by 2, so that means one of those is a double bond. So to make it a double bond, I will take out one pair from each and make that a double bond. And now I have 8 plus 8 plus 8, 2, 4, 6, 8. My nitrogen has 2, 4, 6, 8. My oxygens each have 8, and I've used 24 electrons. So that's a good structure. And then because it's an ion, then it's nice if we can put it in brackets to show the minus charge. That's what you're supposed to do with ions. So show that it has a charge overall, and in brackets is showing that it's an ion. Okay, so that would be for nitrate. Then if we were going to do this one, H3O plus 1, so hydrogen has 1 valence electron. There's 3 hydrogens. Oxygen has 6 valence electrons. So we have 3 plus 6. And now since it's a plus 1 charge, that means we subtract an electron. And again, it doesn't matter where it's from, it's just from the total. So it was 9 and then -1, so we have 8 electrons. So oxygen has to go in the center, hydrogen can never go in the center. And so if we single bond a hydrogen to each side, I would need an unshared pair to give oxygen 8. And 2, 4, 6, 8, I've used 8 electrons, and it's a good structure. Both hydrogens have 2, which is what they need. Oxygen has 8, and it's a +1 charge overall. So that's the only difference for ions. You just adjust the total number of valence electrons. If it's positive, you're subtracting that many. If it's negative, you're adding in extra. Okay. For exceptions to the octet rule, we've said that we're always trying to get 8 for the bigger elements like carbon, nitrogen, oxygen, fluorine, and bigger. So that's still true. We are trying to get 8, and carbon, nitrogen, oxygen, and fluorine will almost always have 8. Carbon will always have 8. Nitrogen almost always. There's a couple exceptions where we end up with an odd number of electrons that nitrogen would maybe only have 7. But for the most part, those guys will have 8, and they cannot have more than 8. They're not big enough. Boron, on the other hand, if we look on the periodic table, boron is smaller than carbon, so it can actually be stable with 6 electrons. Now, it can have 8, but very commonly boron has 6. So that's something that you need to remember, that boron will often only have 6 electrons around it. And then bigger elements than phosphorus, so phosphorus, sulfur, chlorine, and anything larger than that, so as we're looking at the periodic table, anything larger, they could have more than 8 if needed. So we will try to give them 8, but if there's extra electrons, they can handle it. If we look at the periodic table, that is because they have a empty d orbital. Can't really show my periodic table here, but they have an empty d orbital. Phosphorus, sulfur, and chlorine have an empty d orbital because they're in the 3p orbital, so they're not using their d. So that's where the extra electrons could be put if needed. So they can actually, phosphorus a lot of times has 10 electrons around it, and so does arsenic and antimony. But then sulfur and selenium often have 12 electrons. They can make 6 bonds, and that's the highest. No one can ever make more than 6 bonds. No one can ever have more than 12 electrons around it, no element. But it is fairly common for sulfur to have 6 bonds or 12 electrons around it, and phosphorus and arsenic to have 5 bonds or 10 electrons around it. So if we look at the next one, arsenic pentafluoride, there's only one possible way to draw this because fluorine can only make 1 bond. So fluorine could never be in the middle. So arsenic has to be in the middle, and we have 5 fluorines. And fluorine also can't bond to more than one thing. So we couldn't have like arsenic with a fluorine and then a fluorine on the other side. Okay, that can't happen. Fluorine has 7 valence electrons and it's super electronegative. It only makes 1 bond. So that just means we have to bond our fluorines all around our arsenic, and then each one will have 6 other valence electrons. And we'll see if that works out with the valence electrons. So arsenic has 5 valence electrons, fluorine has 7, and in this problem, there are 5 fluorines. So 7 times 5 plus 5, we have 35 plus 5. So we have 40 electrons to use. Did we use 40 in our structure? So each fluorine has 8 around it, and there is 5 fluorines. So 8 times 5 is 40. Yes. So the fluorines are all stable. They all have 8 valence electrons total. And then the arsenic ends up with 10, but it's okay because it's big enough and it has that empty d orbital. So there's one example of an exception. And then for the boron, boron has 6, just 3 valence electrons. Okay, so boron has 3. And then there's 3 hydrogens, each having 1. So that's a total of 6 total electrons to be placed, 6 valence electrons. So again, hydrogen can't be in the middle. It can't be double bonded, neither can fluorine. So both of these have to be just single bonded. So that's why we know that this is the structure. And for this one, I'm using 6 electrons. That's all I have. So I cannot put an unshared pair on the boron. There are those electrons available. So it's just 3 single bonds to hydrogen using 6 valence electrons. So that's a good structure. So always when you're doing the structures, we're trying to give everyone 8, but if there are extra valence electrons, then it's going to be usually the larger central atom that they go on. So SF6 is another example. It's a real thing, sulfur hexafluoride. And if we put the sulfur in the center and the 6 fluorines around it, we'll count up our valence electrons. 6 times 7 is 42, plus 6 more for sulfur is 48. So we have 48 valence electrons from sulfur and fluorine. And then if we put sulfur in the center and put the 6 fluorines around it, all with 8 total valence electrons, 3 unshared pairs to give 6, and then the bonds, that adds up to 48 electrons. So that is the structure. So sulfur ends up with 12 electrons around it, 6 bonds, and that's stable. And that's the most. Nothing could ever have more than 12 electrons around it. Okay. And then I'm asking you to draw the Lewis structure for SO4 minus 2. So once again, you add up the valence electrons. So if you wanted to, you could pause this and try it yourself and then check. So sulfur has 6, oxygen has 6, and there's 4 oxygens. So that's 24. And then it's a -2 charge. So that means we have 2 additional electrons for the -2 charge. So we end up with 32 electrons. Okay, so sulfur's bigger. We put it in the center, and then we can put an oxygen on each side. And then every oxygen needs 8 if it's single bonds. And sulfur now has 8 with the 4 bonds. Each oxygen has 8. And we've used 32 electrons because 4 times 8 is 32. So that's a good structure. We can put it in brackets because it's an ion with a -2 charge. Okay, so that's a perfectly good structure. But the thing about sulfur is it can have more than 8. So actually, while this is fine, and you could have stopped there, sulfur actually could have a double bond to one of the oxygens, and then you would only need 2 unshared pairs on that one, with the other 3 having single bonds. And that is also only using 32 electrons, and each oxygen has 8, but the sulfur has 10, but that's a valid structure. And it doesn't matter if you put the double bond on that oxygen or that oxygen or that oxygen or that oxygen. Okay. Or you actually could also have 2 double bonds, because sulfur can have as many as 12 around it. So you could have a structure like that with only 4 extra electrons on the 2 oxygens that are double bonded and 6 extra electrons on the 2 oxygens that are single bonded. That also uses 32 electrons, and all the oxygens have 8, and this sulfur has 12. Okay, but that's the most. You couldn't do more than 2 double bonds because then sulfur would have too many. So sulfur cannot have more than 12. So it could have 8, it could have 10, or it could have 12. And those are all fine structures. And again, since it's an ion, you should put brackets around it with the charge outside. Okay, so then I have the second paper of problems for you to try, problem set 2 with the Lewis dots.